get back to relativity and do this somewhat mathematically.
100 years ago, a deceptively simple formula revealed a hidden unity buried deep in the fabric of the universe. It tells of a fantastic connection between energy, matter, and light. Its author was a youthful Albert Einstein. It's the most famous equation in the world. E equals mc squared. But while we've all heard of Einstein's big idea, very few of us know what it means. In fact, E equals mc squared is so remarkable that even Einstein wasn't sure if it was really true.
Albert, darling, you're later than I expected. We've only got sausage and cheese tonight. What is it?
We need to talk.
Has something happened?
Oh, no, nothing. Sorry, no. I spent most of the day staring out the window at work, looking at trains. And I started to think about an object and how much energy it had. Can I explain it to you?
Of course you can. But first, dinner, food and talk.
I think the gods are laughing at me.
The gods were not laughing at Einstein. He'd united in one stunning insight the work of many who had come before him, scientists who'd fought and even died to create each part of the equation. The story of E equals mc squared starts long before Einstein with the discovery of E for energy.
You're muted. All right, so give yourself 2 points. So special theory of relativity is related to motion near the light speed. You're going to be moving at a constant velocity in a straight line. So you don't get to speed up, slow down, or change direction. It's a very special case of motion. That's the reason why it's called special relativity. So it's a limited case of motion. All right, so special relativity. So this is the one which is published in 1905. It's a limited case of motion near the light speed. So speed is constant, the direction is going to be constant. Speaking of motion, it's a displacement of mass in space and in time. All right, so you got your mass, you got your space, you got your time. So something happens to mass, space, and time. So this is what the theory is all about. So mass is going to change, time is going to change, space is going to change. All right, whenever you're ready.
The D, last one?
D is the best one. Give yourself 5 points on that one. Guys, you're moving at a constant velocity, which means that you're moving a straight line at a constant speed. So everything that we discuss will be true near the light speed within that reference frame. Those of you guys who picked D, give yourself 2 points.
Imagine if I was sitting still and holding a mirror to my face.
All right, so same question. He's asking this question when he was 16 originally, but he came up with the question because he was studying Maxwell's equations. And Maxwell's equations obviously predict that the light travels at the light speed with respect to a reference point, P. He said, what if the reference point is also moving at the light speed? Would I be able to see myself inside the mirror?
And the light travels from my face to the mirror, and I see my face.
Yes.
However,
and you guys have to understand that at this point, he knows nothing about the Michelson-Morley experiment. This guy is just reasoning.
if I and the mirror were traveling at the speed of light...
You're going at the same speed as the light leaving your face.
Exactly.
The light never reaches the mirror.
So would I be invisible?
All right, so we discussed that before. I'm just going to discuss it and lay down the mathematics for it. For you to be able to see your reflection, obviously the light from your nose has to reach the mirror. So the question is, if the mirror is moving at the light speed, would the light from your nose still be able to reach the mirror, obviously? So that's how things get started. All right, so let's take a look at it from a classical relativity. This is known as the Galilean transformations approach. All right, so you got this object, the car moving away from you at 50 miles per hour, and you throw a stone in the same direction, trying to smash the back window. Stone is also going at 50 miles per hour, right? All right, so you know nothing is going to happen. We discussed that before. All right, so you got this ball thrown in the forward direction at 50 miles per hour. And this ball is going to be thrown in the forward direction in a bus, which is also moving at 50 miles per hour. Okay, now, Postulate number one says the laws of physics will be the same in every single inertial reference frame, something that we discussed yesterday. The inertial reference frame is a frame of reference that's moving at a constant speed in a straight line, or it's simply stationary. All right, so let's get this outside observer. This guy is going to be a stationary observer, and somehow he's able to see the ball. All right, so how fast is this ball moving with respect to this stationary observer? All right, so you do a Galilean transformation. So you add up the speeds. All right, so speed of the ball with respect to the bus's speed with respect to the stationary observer is going to give you 100 miles per hour. So that's a commonsensical way of doing stuff. All right, so Galilean transformation. So this is the speed of the ball, which is going to be 50. So v is going to be the speed of the bus, that's going to be 50. And you end up getting 100 miles per hour. All right, so that's a commonsensical way of actually adding speeds, the way we've been doing it forever. All right, so we will apply the same logic to Einstein's case. In order to solve this problem, Einstein comes up with two postulates. You know what a postulate is right now. It's an underlying assumption. It says that the light speed is going to be constant regardless of your motion. That becomes the second postulate. The first one is the relativity postulate. The laws of physics will be the same in every single inertial reference frame. The second one is he's trying to solve this problem. He's saying that the speed of light is just going to remain constant relative to each and every single observer, regardless of the motion of that observer. Okay, you guys have seen this question before, so.
Both measure the same.
All right,
Exactly.
give yourself 5 points, and those of you guys who take D, give yourself 2 points. Okay, so regardless of which direction or how fast you're moving, light speed will be measured the same in every single reference frame. So if that's the case, the best answer is going to be D. All right, so Galilean transformation is not going to work. Instead, the Lorentz transformation is going to work. So we'll discuss about Lorentz transformation shortly. Let me check to see if we will make an adjustment. All right, Lorentz transformation. I think I missed something somewhere. All right, so this is known as the Lorentz transformation. So this is the light moving at the light speed inside a reference frame, which is also moving at the light speed with respect to an outside observer. Now, instead of getting a speed which is twice the speed of light, if you use the Lorentz transformations, you end up getting the same speed. All right, I am missing something here. Postulate number 2. Okay, this is the one that we missed. All right, let's get back to this one. The argument is, okay, so this is the second postulate that Einstein came up with. Relative to each and every single observer, light is going to move at the light speed. All right, so light is a particle in this one. All right, so it's moving at the light speed. The mirror is moving at the light speed. Okay, so at first thought is because they're moving the same direction at the same speed, you won't be able to see a reflection. So, but if you place the mirror on a wall of some kind of a vehicle that can travel at the light speed, all right, and we had a long discussion about that. The conclusion is, regardless of the motion of the vehicle that you're in, the light is still going to move at the light speed relative to you. So this is going to allow you to be able to see yourself. All right, so Einstein must have come to that conclusion when he was 16. Obviously, the reason why he abandoned it is because of the following. If you apply the Galilean transformation to this, all right, so this is the speed of light relative to Einstein, and this is the speed of light. This is the speed of the vehicle relative to the stationary observer. The speed of light that stationary observer is going to experience for the light that Einstein, for the particle of light which is moving at the light speed relative to Einstein, is going to become twice the speed of light. Okay, so when you're 16, this is when you give up. Basically, Galilean transformation does not work out, because for this to work out, this light still should move at the light speed relative to the stationary observer. All right, so if you're 16, you will give up. If you're a regular person, you will give up. If you're Einstein, however, it's a different story. So Einstein says, nonsense. Light should always move at the light speed relative to any observer, regardless of their motion. That's it. This becomes the postulate number 2. He knows that this sort of mathematics that we use does not work. All right, so he starts to look for the mathematics that fits in well with his theory. Okay. He finds that mathematics. All right, so those are the 2 postulates that we came up with from Hendrik Lorentz's mathematics. Remember, Hendrik Lorentz is one of the guys that was trying to rescue the theory of ether, and they were not able to detect ether, so he came up with Lorentz transformations to explain that the instrument would experience some kind of a contraction in the direction of motion, and that sort of contraction didn't make a lot of sense to physicists. And Einstein looks at that kind of mathematics and he says, oh, that's what I'm looking for, so that's what I'm going to use. So he borrows the mathematics from Lorentz, in essence, and that's the sort of mathematics that he starts to use and develop. All right, so Lorentz's transformation, or these are known as Lorentz transformations. All right, so this is, all right, so this is the light moving at the light speed relative to this reference frame, which is moving at the light speed relative to a stationary observer outside. All right, so this is c, so this one. So what do we have? You got c plus c, it's going to be 2c's. C squared divided by c squared is going to be 2. And simplify it, end up getting the light speed. Okay, now this transformation worked. All right, so the light that moves at the light speed relative to Einstein is also going to move at the light speed relative to an outside stationary observer. That's what it means. So he found his mathematics in Lorenz's work, in essence. Okay, so now that we got the mathematics for it, okay, so there are two formulas that you need to know. Okay, so let's explain what's going on. All right, so this is the speed of this object relative to a moving reference frame with respect to a moving reference frame. All right, V is going to represent the speed of this reference frame with respect to the Earth reference frame. All right, so this is the speed of the moving reference frame with respect to Earth reference frame. And U sub x is going to be the speed of this ball with respect to the Earth reference frame or a station reference frame. Okay, so you guys will have multiple. Okay, I'm not going to give you a written test for the past 2 chapters. Number one, I don't have that kind of time to grade that sort of stuff. So math portion of the test as well as the conceptual portion of the test will be multiple choice. So these are the basic formulas that you need to kind of get used to using. Or if you want to solve for the speed of an object inside a moving reference frame, this formula gets altered slightly. All right, notice that you end up moving u sub x prime with u sub x, and then you end up putting a negative sign in front of the second term. All right, that's it. All right, so let's take a look at an example of this, a couple of examples, so you guys know how to do the transformations. One of them is going to be a simple example. So we have an object that's going to be moving at 88% of the light speed with respect to the spacecraft. All right, so if it is moving with respect to the spacecraft, this is going to be u of x prime spacecraft, and this spacecraft is moving at 60% of the light speed relative to Earth. So it's going to be your v. So how fast is this object moving relative to the Earth? Okay, so this one is going to be straightforward. So this spacecraft is moving at 60% of the light speed relative to Earth. And this object is moving at 88% of the light speed relative to a moving spacecraft. So the question is, how fast is this object moving relative to Earth in terms of light speed? All right, so that's the transformation equation that the first one that we came up with. All right, so just plug the numbers in. So this is going to be 88% of the light speed. This is going to be 60% of the light speed. Okay, notice that you cannot add them up and get more than the light speed. So everything is going to get divided by the term inside the denominator. So that gives you almost 97% of the light speed in essence. Okay, we'll see the same thing in an animation form right now.
So, while Albert will surely agree that Henry throws one heck of a fastball, he can always throw a little light on the matter. And be sure it'll get there first.
Even along the direction of relative motion, components of velocity never add to a speed greater than the speed of light.